Hi everyone, my name is Dennis, and today I present a project about reducing complexity in diffusion and flow models. Recently, diffusion models emerged as a successful alternative to autoregressive models due to several reasons. First, fast parallel token generation versus sequential in autoregressive models. Second, built-in error correction and quality control using iterative denoising. And lastly, they inherently support multimodality due to integration of continuous and discrete tokens. However, they still have challenges. Until recently, they didn't scale to large language modeling, and second, iterative denoising is still costly and suboptimal in many cases. So in this project, we propose few-step generation to address the last challenge. In particular, we propose a few-step generation method where, unlike prior methods, we focus on minimizing number of time steps as well as the neural network depth. Diffusion models are equivalent to continuous normalizing flows where sampling can be done by integrating an ordinary differential equation from time 0 to time 1. Typically, the time variable is discretized and integration is replaced by summation, which is equivalent to fixed time Euler's ODE solver. There are a number of methods that minimize number of time steps to reduce sampling complexity. Our main idea stems from the fact that recent neural network architectures consist of a sequence of transformer blocks. Then we can rewire these blocks to solve an inner ODE with respect to its depth. We introduce residual connections, which naturally implements a fixed-step Euler solver. Previous few-step sampling methods are fully compatible with our extension with minimal architectural changes and negligible computational overhead. However, training objective requires more deliberate steps. To support our extension, we introduce length consistency term with a teacher target and student subnetworks. The elements of this term are concatenated with conventional training objective. In image generation experiments, our method shows minimal sampling quality decrease while substantially reducing the number of enabled neural network blocks. Our latency scaling curve shows that we can achieve 2x latency reduction in the most efficient sampling regime, or we can show that our method with adaptive step solver scales better in high quality sampling regime. In this presentation, we introduced recent diffusion versus autoregressive model trends. Diffusion models have been dominant in data domains with continuous representations like images and videos. Autoregressive models are still dominant in large language modeling with discrete tokens. Now, diffusion models emerge as an alternative for language and ultimately multimodal LLMs. Fast generation is the main advantage and opportunity in diffusion models. Current few-step sampling methods show promising effectiveness in time dimension. We proposed a generalization to the neural network dimension. Our method showed improved complexity quality trade-off scaling. It also introduces unique opportunities, which we consider as the future work. If you have any additional questions, please come to our poster and I will try to answer your questions.